let's look at what we call the OA operators here for rotations. And with these we can act on functions from R3 to, say, complex numbers. So how did we define these OA operators? Let's say OR, if R is a rotation matrix, acting on some function f, evaluated at x, that's just f evaluated at R inverse times x. And let's say, and this R some SO3 matrix. So we want to view these operators as the group elements. We could also say, instead of viewing this as a group, we could say this is a representation of SO3 on some function space, say on continuous functions, continuously differentiable functions. We want to take derivatives soon on R3, something like that, or some other suitable space. But never mind for the moment. So let's look what happens if we still have this rotation about the z-axis over here. So let's look at this as an example. So ORZ of phi applied to some function f, and let's say evaluated at x, y, z. What's that? That's f evaluated at RZ of phi inverse times x, y, z. And what's the inverse? The inverse is just rotation with the opposite angle, phi instead of minus phi, same axis, applied to x, y, z. Now we can read off the result by looking at this matrix up here. If we send phi to minus phi, what happens? The cosines are invariant, and these sine terms here, they change the sign. So we get f of, what will that be? X times cosine phi plus y times sine phi, and then we have minus x sine phi plus y cosine phi and z. And now if we are interested in a generator, if you want to go from the group to the Lie algebra, we would look at this object here. We would say minus I d phi of our group element, Rz of phi. Let's look how this acts on, let's say, some, and then at phi equals 0. But let's act with this on some function f, evaluated at x, y, z, and then the whole thing at t equals 0. So what's that? Just copy the minus I. So if we take the derivative with respect to phi, we have to take the derivative of f with respect to the first and the second argument and use the chain rule. So we get what? There's a df dx evaluated at the same thing as before, let's say Rz of minus phi x, y, z. And then from taking the derivative of this here, we get a minus x sine phi plus y cosine phi. And now there's a second term, that's df dy at the same argument, Rz of minus phi times x, y, z. And now we have to take the derivative here, and that gives us a minus x cosine phi minus minus y sine phi. Okay, close this big braces here, and then the whole thing at, what did I write here? T equals 0. That was a phi. Our parameter is called phi here, so the whole thing at phi equals 0. Now at phi equals 0, the rotation matrix is the identity. That is what we get here is, I take this minus sign in here. Okay, so this here is just x, y, z. Forgot some bracket here. And here the sines go away, the cosines are 1, so we get just the y from here and the minus x from here. And now let's use this minus sign in order to swap the terms. So I have I, and now I want to write this as x d dy. That's from the second line, minus y d dx. And the whole thing acting, write it as a differential operator, acting on f of x. Now we see that this thing here, that's the generator, that's in our Lie algebra now. And if you know some quantum mechanics in physics, you would recognize this object as a component of the angular momentum operator, the z component of the angular momentum operator, except for the prefactor here. And actually this is an example for why we chose this funny convention with the I in the definition of the Lie algebra, because then the objects that live in the Lie algebra are objects which appear as self-adjoint operators, or in the finite dimensional case, Hermitian matrices, and these are objects which physicists are used to work with, so that's why we have this funny I definition here.